Ready for some optimization? Woo! For good and bad, this right here is actually maybe most of the entire reason that for your major, whatever it is, you were required to take calculus. So the real world is always all about optimization. I'm looking to make it cheaper, faster, smaller, bigger, lighter. But most of the time, optimization is really what we're trying to do out there. Saving money and saving time being the two biggest things. Optimization problems at their heart are just saying we are trying to find those relative maxes and mins. Or given some sort of constraint, we're trying to find an absolute max or a min. We already know how to do that. We just need an equation to take the derivative of it. What makes optimization really fun is usually we're not given an equation. Usually we're given some sort of context and we have to build an equation out of that context. So I'm going to use the props I have available to me in the room. It's the box. And somebody had to design this box. And whoever designed this box, trying to see if it's got some recycled paper content, not that I can tell, but someone had to design this box. And if they were trying to make this box as cheaply as possible, what do you suppose they were trying to optimize? Oh, I should say there's another issue here. Someone decided that the box needed to hold 50 masks. So there was some amount of volume that we had to be able to contain. We needed to fit 50 masks in it. But there were other shapes of boxes they could have chosen. And I bet someone worked an optimization problem that ended up with exactly this shaped box. So I'm gonna fake some stuff. Let's say that I needed to build this box. Oh, and I know I kind of asked a question. I didn't mean for it to be rhetorical, but then no one answered it. So sorry, since it's here and it's empty, I'm taking it apart. So, give me a second. This is what someone optimized. Someone figured out how little cardboard could be used to construct that box. Now this is an optimization. Check it out. We cut corners out of it. There are like all of these notches. I guarantee someone figured out, now really they probably did it by trial and error. They probably did not write a calculus problem. Who am I kidding? But somebody figured out that they could make this thing lighter. They could use less material. It didn't have all these things in it. Okay, back to something that we can tackle as a calculus problem. Let's just say that my thought was, we're gonna try to build this box. I need this rectangular box. I'm gonna need it to hold I'm gonna need it to hold 54 cubic inches is what I meant to write, but we'll just turn that into a C. I need it to hold 54 cubic inches. Now, there are other, I need this rectangular box to hold 54 cubic inches. I'd like to find the box with the smallest surface area. Now I'm going to add one other constraint in here, and we all know that this box did not magically arrive in this room. It probably, based on the fact that it was constructed in France, it probably got here on a boat and then on a truck. So the reality is there's probably some other constraint on this box, not just volume. So I'm going to say that for packing into the shipping container, it needed to have a square end. So I'm going to say the box with the smallest surface area and a square end. Oh, and what does it mean to find, this is a little bit vague, find the box? I don't know, maybe that's the vagueness that your instructor would use. But we're going to find the dimensions of the box. How about that? Of the box with the smallest surface area and a square end. So I said that most of the time with these optimization problems, the hard part is coming up with the equation. We know how to take a derivative, set it equal to 0, do our number line thing, all that good stuff. So to find the equation, I am always going to hone in on what is the word that ends in EST. Now, it doesn't literally always end in EST, but what's the thing we're trying to optimize? In this case, the thing we're trying to optimize is the surface area. So I'm going to start by writing an equation for surface area. And I'm going to go ahead and draw our box. I don't draw super well in 3D, but I do take boxes apart really well in real life. I hate cardboard. No, I don't hate cardboard. It's just, I wish we didn't have so much cardboard from shipping stuff. So I said that it needed to have a square end. So if I called this side X, this side would also need to be X in order that to be a square end. But this length could be something different from X. And in fact, it is in our real life box. So I'm going to call that Y, which means that when I go to find the surface area of this thing, the surface area is me adding the areas of all the sides. Well, this front side of the box is a rectangle that's Y by X. But that's the same as the back side of the box that we can't see is also Y by X. And the top of this box is also Y by X. And you know what? So is the bottom. So all told, I've got 4 of those. And then we've got those 2 end pieces that have an area of X squared. Now I've got this formula, right? I've got my surface area is equal to 4xy plus 2x squared. And I look at that and I'm like, yes, I have an equation. I know how to take a derivative and set it equal to 0. Oh, darn. We have 2 variables. I sure hope we know something else. And that's the key to every optimization problem. There is something else we know. That something else is usually a constant. And in this case, the only other number we've got in here is 54. Well, if it needs to hold 54 cubic inches, don't put the cube on that because it was weird to say inches, 54 cubic inches, then that's volume. And the volume of this thing is Y times X, or Y times X squared. So I need this to hold 54 cubic inches. And if it's going to hold 54 cubic inches, then this becomes, sometimes we call it the constraint. I've heard people refer to it as our helper equation because it's going to help us to get rid of the y over here. It doesn't actually matter which letter I solve for, but if I tried to solve for x, I'd end up with a square root. And none of us wants to take a derivative with a square root if we can avoid it. So I would choose to make this say y is equal to 54 divided by x squared and plug that in over here. That's going to turn my area equation into 4x times 54 over x squared plus 2x squared. And per usual, I'm going to choose to clean it up before I take a derivative if I can. So one of those x's will cancel out. 4 times 54, let's see, 4 times 50 would be 200. 4 times 4 is 16, so 216 x to the negative 1 plus 2x squared. Now we've gotten finally to the really calculus-y part. So go ahead and on your own, take a derivative, set it equal to 0, get your number line going. Let's see if we can find those relative maxes and mins. Hopefully the relative minimum, since we were looking for the smallest surface area. Hopefully we wrote a problem that has a relative minimum. Fingers crossed. Did we find any critical points? Are they gross? I have no idea. Well, if it factors great, I think you're going to need a common denominator because you got fractions. Yeah. But at least, oh, it worked out. Negative doesn't sound good. I think you're okay. I don't think you have a negative. I mean, there's like a negative in there, but I think once you move it, it's gonna work. Just so we can do the algebra together, your choices are to like factor out an x to the negative 2, which I think is a little bit weird, but totally works. Or to think about these as fractions and get a common denominator. I don't actually care which version we play. What do we think? Did any of you find a common denominator or did you factor? Okay, let's go common denominator then. So I'm going to write that as negative 216 over x squared plus 4x squared over x squared. If I multiply the top and the bottom, nope, x cubed, 4x cubed. Does that sound better? 4x cubed, multiplying the top and the bottom of the 4x piece by x squared. So on top, well, it doesn't matter. If I put all of that together, I've got negative 216 plus 4x cubed all over x squared. Now, if I set that equal to 0, a couple things to note. X equals 0 would make this undefined. But also we had an actual box. If x were 0, we have problems. We don't actually have a box. So x equals 0 is kind of like that boundary point. I can't actually go to x equals 0. So if I focus on the numerator here, negative 216 plus 4x cubed is equal to 0. I would just move the 216 over. So x cubed would be 54. Which would make x the cube root of 54, which we could simplify a little bit if we wanted to, but I wouldn't worry about it. This is where, when we're doing these optimization problems, right? Then when we were doing this as an increasing, decreasing relative max min thing, we would find that and then like get a number line or a sign chart and have these test points. The nice thing about doing optimization problems is because of our real world context, we can think about this actually as an absolute maximum or minimum problem. When we have absolute max or min problems, all we have to do is check the endpoints and check our critical point. Additionally, we can think about, and this is my favorite way to decide that that's a minimum, is to just take the second derivative and plug that in to see if we get a positive number or a negative number. So those are three options for how to decide whether it is really a max or a min. So if I go by the second derivative test, if it's going to be a relative minimum, I'm hoping that my second derivative works out to be a positive value. So I'm going to find a double prime. If I bring that negative 2 down, 2 times 216, that would be 432. My negatives will cancel out, and I've got x to the negative third plus a 4. Remember, I don't care what the number is. I just have to figure out if it's positive or negative. Sure looks like it's going to be positive to me. So that second derivative evaluated at the cube root of 54, whatever it is bigger than 0, which is good. That means that we're concave up, which means this represented a minimum. And then kind of similar to what we had to do with related rates problems, I do want to be careful about units and sort of how I'm reporting out that final answer. And if we had to find the dimensions of the box, that means I've got to give an x value and a y value. So I would say that x is equal to the cube root of 54 inches. And y, I'm not going to bother simplifying it, but if I want to know what y equals, I'm going to look for an equation that I already solved to say y equals. And plug it in. So 54 divided by the cube root of 54, whole thing squared, inches. Now I'm actually really curious. Obviously, I faked the dimensions of the box anyway, but what is the cube root of 54? 4, 2, 1/3 power. Okay, so the cube root of 54 is like 3.78-ish. And that is about to get ugly. That thing squared. Nope. Okay, I was trying to do this quickly. Clearly a real calculator would be helpful, but since I don't have one, 54 divided by, I got this. 3.78 squared. Oh, that's interesting. Okay, so if we had just gone on, clearly the manufacturers of this box did more than just surface area. We did not end up with the magic dimensions of this box. It's okay. So it was a good thought. Shall we do another optimization problem for more practice? Okay. I won't take apart any more boxes this time. For this one, how much time do we, okay. This is like a really classic problem. No, this, we'll go with this. This is a classic problem, but something that's a little faster to figure out. We want to find a positive number for which the sum of its reciprocal and 4 times its square is as large as possible. Some of the optimization problems in the book are really just kind of like this. They're not even pretending to be real world-ish. We're just doing some stuff with numbers. How do I know it's an optimization problem? Because I've been asked to make something as large as possible. Where do I start for finding an equation? I need an equation for this thing that it's telling me to make as large as possible. So I'm just going to start writing the pieces. The sum, so I know I'm going to have addition of its reciprocal. Well, I guess I need something to call the number. I'm going to call the number n because it's a number. So the reciprocal of that number is 1 over n. And 4 times its square. So 1 over n added to 4n squared. And that's the thing we're trying to make as large as possible. So I don't really know what to call it. I'm just going to call it f because that is now my function. This is accidentally fairly similar in form to the one that we just did, but without the context. So I have this equation, but it's already in terms of one variable. Sweet. We can just take a derivative and set it equal to 0. How are we doing? We got a derivative. So I'm going to say my derivative looks like negative n to the negative 2 plus 8n. And I'm going to do the same thing we did last time and get a common denominator. So that's negative 1 over n squared plus 8n. But I'm going to make that 8n cubed over n squared. So I've got 8n cubed minus 1 all over n squared. Same kind of thing as last time. We know that we need this number to be positive. 0 is technically not positive. Also, 0 would make this thing undefined, so that would be bad. But if I set that equal to 0, I think on top, I'm just going to get 1/2. I don't know how picky your instructor or realistically the TA grading things is going to be, but I would say we should still show that this is as large as possible, meaning I would want to show that my second derivative worked out to be negative if this is going to be a maximum. So when I take that second derivative, negative 2 times negative 1 will make that a 2n to the negative 3 plus 8. And if we plug in that n equals 1/2, then my second derivative at 1/2 would look like 2 divided by 1/2 cubed plus 8. I'm getting nervous. That looks positive to me. Maybe someone wrote a bad problem. I stole this problem from a random worksheet that was laying in the classroom again. Looks to me like that's a positive number, whatever it is. And if my second derivative is positive, that would imply that this thing was concave up, which would mean that we actually just found a minimum. Let's resolve this. If I graphed this thing, like if I just thought about f of n for a second as being 1 over n plus 4n squared, if I don't put an upper bound on this, this can be as large as possible, right? Like if I don't, this part's going to go to 0. But this part goes to infinity. So this is a poorly written problem that I found randomly in the classroom. 2 ways to fix it, we could say, is as small as possible. The other option for fixing it would be to say there is no such number. Cool. Good times. That's what I get for using random problems from the classroom.
Most of the time, though, we get a problem fixed in the secondary. Like what we want it to show.
Yes. The only time that I've seen it not work out that way is if you were given an additional constraint. So like on this problem, if this had said, find a positive number less than or equal to 10, and all of that same information, then getting the answer that we just got would mean that we would have to say, oh, well, the number that we should use is 10, not the thing that we just found, because the thing that we just found was actually a minimum, not a maximum. So there are some problems that are going to work out like this, where we're going to have to know that the final answer would be that n is equal to 10. But other than that, all the rest of them, it usually works out that whatever point you found as a critical point is the correct thing you were looking for. It's a max if you were looking for a max, or a min if you were looking for a minimum. Yeah. I think we should call it a day.